I want to start by giving some examples. I'm not going to give the actual definition of an arithmetic group until tomorrow, but we'll get the idea of what it means just by looking at a few simple cases. After that, I'm going to explain just briefly why it is that geometers would be interested in arithmetic groups. And then after that, I'll start talking actually about arithmetic groups. So first of all, it's interesting, to a topologist, the first questions you ask about a manifold is whether it's compact or not. And we'll answer that question in terms of arithmetic groups two different ways. That'll be maybe the main thing I talk about today. But then after that, I'll talk about just some basic properties of arithmetic groups. And like yesterday, maybe there's too much here to do, but that's okay, because nothing I do today is really needed for the talk tomorrow. So I'm just going to be doing, tomorrow's talk is independent, but I wanted to talk about some very important concepts in the theory of arithmetic groups today. And so let's just start by looking at some examples. In arithmetic group, it's the same kind of thing I was doing yesterday. We take the integer points of some group. So the simplest example, or maybe a most basic example of an arithmetic group, would be to let gamma be just the ordinary special linear group, but only the integer matrices. That's what makes an arithmetic group, is that we're only taking integer points of the group. And just to make sure we're all clear on this, SL3Z means the 3 by 3 matrices of determinant 1, and the reason we want the determinant to be 1 is that this should be a group under multiplication. And so to be a group, well, you need to have inverses, and you can calculate the inverse of any matrix by taking the adjoint matrix, you look at these cofactors, and then divide by the determinant. So it's a fact that a matrix over a ring is invertible if and only if the determinant is a unit in that ring. So actually, if we wanted to make a group here, we could allow that the determinant has to be either 1 or minus 1, but for simplicity, I'll just take the matrix of determinant 1. But those are all invertible because you can, take the inverse, just calculate this cofactor thing, divide by the determinant, but the determinant is 1, so it's easy to divide by that. So all these are invertible as integer matrices. In other words, this is a group. But I'm not going to dwell on this, so let me just say it this once. When I talk about groups, the groups I'm talking about are large, they're infinite. I don't want to get into a lot of technicalities dealing with just finite cases, finite groups that are involved in there. So when I say gamma is SL3Z here, well, really it might not be SL3Z, maybe it's a subgroup of finite index. So maybe throw away some finite group instead of taking all of SL3Z. Anyhow, that to me is the most basic example of an arithmetic group. But if I'm talking to hyperbolic geometers, which I think maybe I am, then probably the basic example is not SL3Z, but we should take the integer points of a hyperbolic type group, maybe SL13. So this here means the integer points of SL13. So we just take all of the matrices in the Lie group SL13, but only the ones with integer entries, and we can say that more explicitly. It's just this condition here says that the matrix is an SL13, where, that I13 matrix is the usual quadratic form of type 1-3, but we only take the integer points in that group. If I made that R, then I'd actually have SL13, but I take the integer points of SL13. And the last thing I should say is over here, I put a dot above the equal sign. That's because, it might not actually be that whole group, it might be a finite index. But again, I don't want to spend a lot of time talking about that. If you're confused about whether it means something that I say, well, ask. But in this case, I really mean it might not be the whole thing, but it could be finite index. I'm not going to worry about passing a finite index. But those aren't the only arithmetic groups. I said gamma should be an arithmetic group. Well, it's something like that. That's the thing. It's some group, and then you take the integer points. So let me just say that briefly. In general, to say that gamma is an arithmetic group means it's the integer points of some group G. So I'll just put a Z as a subscript to mean to take the integer points. And that just means, instead of looking at all of G, just take the integer matrices that are inside it. And that's what an arithmetic group is, except you can't always do this. Sometimes you take G, the integer points of a group G, you get something that just isn't interesting. So there's some conditions. You only look at suitable groups G, but for example, SL3R is fine, SL13 is fine, okay. We'll talk tomorrow about the technicalities here. But anyhow, if you got a nice group, if you look at the integer points, that'll be an arithmetic group. But I hope it's okay to wait until tomorrow to explain exactly which G's you're allowed to use. So for now, let's just look at some examples. And then the crucial thing is, if you form GZ, if you take an arithmetic group, then always the arithmetic group you get is going to be a lattice in G. That's a very important fact. And so let me just remind you, I said this yesterday, but let me remind you again what a lattice is. In fact, I was wrong yesterday. The definition I gave yesterday wasn't quite right. First of all, all, though, to say that gamma is a lattice in G means that it's a discrete group, but I think that's obvious. When you look at matrices with integer entries, there's no accumulation point. This is a discrete set. And so if you take some subset of the set of all integer matrices, it certainly has no accumulation point. So it's obvious that gamma is a discrete subgroup. And then the other thing, I said a little bit wrong yesterday because I didn't want to worry again about details. Yesterday, I only looked at co-compact lattices. I said that everybody was within finite distance of gamma. So yesterday, when I talked about lattices, G mod gamma was always compact. But that isn't necessary for lattice. The next best thing after being compact is, well, everybody knows from analysis that any compact set always has finite measure. Compact sets have finite measure. And so that's what we'll assume. Instead of assuming that this quotient is actually compact, a lot of the things you can do for a compact space, you can also do if the space has finite volume. Right? So, or finite measure. So there's a natural volume on G mod gamma. There's a G invariant volume there. And so if you take the volume of the whole manifold, that should be finite. That's what makes this a lattice. But if that's confusing you, just think of it as being compact. In a lot of cases, G mod gamma will actually be compact. You like that better. But the technical definition of a lattice allows more than compactness. It allows the thing to be finite volume. Right, so that's it. So this is a very important theorem. It's the theory of reduction theory for arithmetic groups that says that every arithmetic subgroup is going to be a lattice. And that makes it, well, okay. So yesterday I constructed lattices by taking integer points. Well, this says that that always works. You always do get a lattice that way. But let me talk about why geometers might be interested in lattices. And it's because they're closely connected to locally symmetric spaces. And so first, let me just remind you what a locally symmetric space is. But before I talk about locally symmetric spaces, let's talk about symmetric spaces. If you look at just the Euclidean space Rn, that's a symmetric space. What that means is, first of all, it's homogeneous. Every point of Rn looks like every other point of Rn. As a Riemannian manifold. The isometry group of Rn is transitive on the space. So that's a homogeneous space. The next thing, that's just what it means to be a homogeneous space. To be a symmetric space means there are isometries with special properties, so there's some isometry in the space that has a fixed point that's isolated. So the fixed point set isn't a line, but there's a point that's fixed by this isometry, and no nearby point is fixed by that isometry. And maybe I should say, so there's, well, in fact, yeah, let's just do an example here. So in this case, for Rn, the isometry is easy to find. Just to find phi of x to be minus x, well, if you try to solve the equation phi of x equals x, that says x equals minus x, so x is equal to 0. The only fixed point of this isometry is 0, so there's no fixed points nearby. So this is an example of an isometry that has an isolated fixed point, but just as a remark, I could have made this definition a little differently. It's a homogeneous space. So if there's some point that's fixed by an isometry, then in fact every point is an isolated fixed point of an isometry because all points look exactly the same in this manifold. The space is homogeneous. But anyhow, this is an example of a symmetric space, and I think most Riemannian geometers would agree that these are the best manifolds. Symmetric space is the nicest manifolds. They have very beautiful properties. Okay. But that's just one example. Another example is maybe of more interest here. Rn is too easy, but I think hyperbolic space is something of interest to people in this room. That is also a symmetric space. It's certainly the isometry group. Well, it's SO1n, that acts transitively on hyperbolic space. And then the other thing is that, again, if you in the right coordinates, phi of x equals minus x will be an isometry, and that only fixes the point 0. So I'm not going to dwell on this. I'll just leave it as an exercise. But that's another interesting example of a symmetric space. There's lots more examples, but they all look pretty much the same to a group theorist. Anytime you have a symmetric space, well, first of all, I'm going to assume my symmetric spaces are always connected. If you let G be the isometry group, well, we know by assumption that the isometry group is transitive on X. Okay? So what that means is, well, any homogeneous space is always just a quotient space, it's a coset space. There's some subgroup of G just from the fact that Gx transitively means that you can think of the space as just being cosets of some subgroup. And then the other thing, though, is K is not just any subgroup. Because we're talking about a Riemannian manifold and K is the stabilizer of a point, well, the stabilizer of a point in a Riemannian space is always a compact subgroup. So always, if you have a symmetric space, it always looks like G mod K, where K is some compact subgroup. But actually, yeah, this is very easy because this doesn't even use really the fact that it's a symmetric space. It's just that X is homogeneous is all you need to get this. So that's what all symmetric spaces look like. I guess that's the summary. Let me just summarize what we've done on this page. A symmetric space always looks like G mod K, where K is compact. But I want to go beyond symmetric spaces and talk about locally symmetric spaces. And my definition might not be right. I think it's right, though, if I just assume that whenever I say locally symmetric space, I mean one that's complete. And then I think my definition is right. I'm just going to say that M is locally symmetric means that, well, it's supposed to mean that locally it looks like a symmetric space. So the universal cover then actually will be globally a symmetric space. So to say that M is locally symmetric to me just means that the universal cover is a symmetric space. And because the symmetric space looks like G mod K, well, no, I guess so. What that means is that we take the symmetric space and mod out by some group of deck transformations. And to get a Riemannian manifold, those deck transformations have to be isometries. Oh, shoot, that's not right. Gamma, these should be isometries of X, not of gamma. I'm sorry, I just wasn't paying attention to what I was doing. So we take isometries of X. Well, the deck transformations, of course, have to be a discrete group. And then again, there's this little problem about that also I should assume that there's no elements of finite order. Gamma needs to be torsion-free, or instead of a manifold, you get an orbifold. But again, I don't want to worry about details like that. But if there's questions, let me know. But anyhow, that's the situation. If you take a discrete group of isometries, torsion-free discrete group of isometries of X, modding that out will give you some locally symmetric space. All right, so for example, if we let G be the isometry groups of Rn, the isometry group of Rn, which is just, well, there's translations and there's rotations, and then you can combine the two, those are the isometries. Then K, if you want to get a symmetric space, it turns out you should take K to be a maximal, not just any compact subgroup, but the largest possible compact subgroup, which is this entire SON. And then when you mod out the space X, it's G mod K. Well, if you take this group here and then mod out the SON part, all that's left is exactly Rn. So this is how we get Rn as a symmetric space. But then I want to make a locally symmetric space. So for that I need some group gamma. I need a discrete group of isometries of Rn. And the easiest one maybe is just look at right inside of here, just take Zn. Just take the integer translations inside of Rn. And then the quotient space, well, you take it's Rn modded out by Zn. I think everybody recognizes that. That's just the torus. So the torus is a very simple example of a locally symmetric space. Something more interesting, maybe, is instead of letting G but the isometries of Rn, the isometries of a more interesting symmetric space like hyperbolic space. So if we let G be the isometries of hyperbolic space, the maximal compact set subgroup will be SON again, same subgroup. When you take G mod K, well, SO1n acts on hyperbolic space with a stabilizer. Well, that is the stabilizer. That's what we said. So we're getting hyperbolic space again. Now to get gamma, well, I'll do the same thing I've always done. If I want to get a discrete subgroup of a group G, I just take the integer points. So I'll just let gamma be SO1n, just the integer points of that. Then the corresponding locally symmetric space will be some quotient of hyperbolic space. That's what a hyperbolic manifold is. So hyperbolic manifolds typically are not symmetric spaces because they've got a fundamental group. You mod up by some gamma, but a hyperbolic manifold is the basic example of a locally symmetric space. And so the theory I talk about applies not just to hyperbolic manifolds, but to more general locally symmetric manifolds. But if you want, just think of hyperbolic manifolds as the things I'm talking about today. Alright, so we've talked now about locally symmetric spaces. A locally symmetric space you get by taking a group G, you mod out by K to get a symmetric space, and then you also mod out by gamma on the other side to make it locally symmetric. That's it, okay? And the key thing, though, is that locally symmetric spaces, well, they come in all kinds of types, and the best ones, as I already said, I think, is the ones that are compact. Everybody liked the manifold, so compact hyperbolic manifold or compact locally symmetric space are what we'd like to talk about. But it turns out that, as I said earlier, sometimes we don't require the manifolds to be compact. The next best thing is to take finite volume manifolds, and that's really what we're going to do. We want to construct finite volume locally symmetric spaces that includes all the compact ones, but it's got some more as well. And let me remind you, as I already said today, that to say that gamma is a lattice in G means that gamma is discrete and G mod gamma has finite volume. Well, it's just an exercise, I guess I call it a proposition here, that if gamma is a lattice in G, and I want gamma to be deck transformation, so I'm going to assume also I have to say that there's no elements of finite order. But if gamma is a lattice in G, and you construct the symmetric space corresponding to G, let X be G mod K, then if we take X mod gamma, that's going to be some manifold. In fact, it's easy to see it's locally symmetric. That's the definition of locally symmetric. The universal cover of this is X. But the key is, if G mod gamma has finite volume, then X mod gamma will also have finite volume. So this will be a nice locally symmetric space. It's a locally symmetric space of finite volume. So the upshot of this, what I've been trying to say, is just that lattices are the fundamental groups of finite volume locally symmetric spaces. That's the key thing. That's what lattices are good for in terms of geometry, is that they're the way, if you want to construct a locally symmetric space, you need to find a lattice in some group G. And it's not easy always to find lattices in groups G, but there's one way that's easy to do it, taking arithmetic subgroups. The point is that arithmetic groups are the lattices that are easy to construct. If a lattice is not arithmetic, it's very difficult to find usually. But if you want to make a lattice, just take an arithmetic subgroup of G, and from that lattice you get a finite volume locally symmetric space. That's the geometric motivation for studying arithmetic groups. Okay, and so then, with that in mind, let me talk about one of the geometric properties of locally symmetric spaces. So here's the situation. We've got a symmetric space, G mod K. You mod out by some lattice to get a finite volume locally symmetric space. And always today, I'm going to assume, I'm not interested in like Rn. A torus is not an interesting space for us today. We want to look at things more interesting. We want to look at hyperbolic manifolds and generalizations of that. So I'm always going to assume now that the universal cover X, the locally symmetric space, is not just Rn. I'm always going to assume X is not Rn. And in fact, I'm going to assume that X doesn't even have Rn as a factor. So X, my symmetric space always, is not a product of something with Rn. There's no flat factors. I'm not interested in Rn at all. And the second thing also I'm not interested in, spheres are examples of symmetric spaces, but that's not what I want to look at. I want to look at things like hyperbolic space. So I'm going to assume that the universal cover is not just a sphere or something like it, and as before, not just that it's not a sphere, but it's also not a product of something with a sphere. So that's the kind of symmetric space I want to look at. And algebraically, what that means is that the isometry group, G, the isometry of X, will be a semi-simple group. That's the kind of group I'm looking at. And because there's no compact factors in X, the group G will have no compact factors. And also, since there's no abelian, well, if there's no Rn in my symmetric space, there will also be no Rns inside of G. So G will have trivial sector. Again, these are technical points. But to group theorists, this is what I'm assuming. I'm assuming that my isometry group is a semi-simple group, rather than being just abelian or solvable, something like that. Okay, and then in this situation, well, in fact, not just in this situation, in general, if you have the fundamental group of any topological space, it gives you some topological information about the space. For any space, the fundamental group is one of the important things that all topologists learn about. In fact, all mathematicians learn about the fundamental group, because it tells you something about the manifold. But the thing is that in this situation that we're in, where we have a locally symmetric space, and remember, all my locally symmetric space have no flat factors and no compact factors. In a situation of locally symmetric spaces, the fundamental group does much more than just gives you some information about the space. It tells you everything about the space. It completely determines all of the topology of X. Just knowing the fundamental group of X will tell us all of the topology of X. It tells us exactly what X is up to homeomorphism. And more than that, not just up to homeomorphism, but up to isometry. It tells us all the topology and all the geometry of the space. And there are some exceptions, which I'll explain in just a minute. But in almost all cases, just knowing the fundamental group of M tells us exactly what M is. And that's a very famous theorem. That's the Mostar rigidity theorem. So let me state that correctly for you. So let me state the Mostar rigidity theorem just says that the fundamental group tells us everything about the manifold. You can't, well, okay, let me just say it here. So the theorem says that suppose you have not just one locally symmetric space, but two of them. So I've got an M1 and an M2 that are locally symmetric spaces, and I'm always assuming, well, finite volume locally symmetric spaces, and those basic assumptions, no compact factors, no flat factors in the universal cover. And also, I need to assume a couple of simple things about M1. First of all, the theorem fails in dimension 2. So I have to assume that M is dimension bigger than 2. And the other thing is that there's a problem if M is not just dimension 2, but it's something cross a manifold of dimension 2. So let me just assume that M is not a direct product. I'll assume that M is irreducible. M is irreducible. It just means, let's assume that M1 is not a product of two smaller submanifolds. And actually, all we need to assume actually is that there's no two-dimensional factor. But let's just say, easiest thing is let's just assume that M1's not a product at all, and it's reasonably big. It's at least three-dimensional. Then the theorem is that if the fundamental group of M1 is isomorphic as a group to the fundamental group of M2, so if M1 and M2 have the same fundamental group, then in fact M1 and M2 are exactly the same manifold up to isometry. Same topology, same geometry, same everything, except this isn't quite right because if you take M1, you can multiply the metric by 2 and make it, instead of making a manifold of volume 1, make it a manifold of volume 2. So you have to, this is true if you first normalize to make them have the same volume. That's the only exception. Okay, that's it. The topology and geometry are completely determined by the fundamental group of the manifold. And this is supposed to, I mean, if you haven't seen this before, this is supposed to be surprising. Usually it's easy to make lots of different manifolds with the same fundamental group, but not if you make them locally symmetric. That's the thing. Locally symmetric with no compact or flat factors. Okay? And so what this means is that everything about the geometry of M somehow can be found inside the algebra of the fundamental group. So all of the geometry actually is determined completely by the algebra. Or another way of saying the same thing is that if you're a geometer, you'd be interested maybe in studying locally symmetric spaces. So if you look at all the irreducible locally symmetric spaces, that's a geometric interest. Well, it turns out that's exactly the same as studying an algebraic problem, understanding the algebra of some groups, namely irreducible lattices in certain semi-simple Lie groups. So a geometric problem, understanding locally symmetric spaces, actually can be converted completely into an algebraic problem, understanding the fundamental groups. That's what the Topology theorem does. And that's all I'm going to say about it. But anyhow, it's supposed to say that these arithmetic groups, these lattices typically will be arithmetic groups, so what that means is trying to understand geometry comes down to understanding these arithmetic groups. Every property of the manifold somehow can be found inside the fundamental group, something algebraic about the fundamental group. And so I want to start by talking about the most fundamental geometric property or topological property of the manifold. I've already said this. The first question a topologist might ask about a manifold is whether it's compact or not. So let's answer that question. Okay, so somehow there's some property about gamma that tells you whether or not M is compact. And I want to tell you what that property is. And actually, I'm going to give you two different versions of the same property. That's called the compactness criterion. You want to figure out what it is about gamma that tells you whether or not M is compact. Okay, so the first thing is just a simple observation. And in fact, I've already used this fact. If you've got a locally symmetric space, so that's X is a symmetric space, you mod up by gamma to get a locally symmetric space. And X then will be G mod K for some G and some K. M is compact if and only if, and this is just essentially obvious if you think about it the right way, M is compact, well M is X mod gamma, that's going to be compact if and only if G mod gamma is compact. And the reason is just that, remember, M is X mod gamma, but X is G mod K. So M is just what you get by taking G and modding out both by gamma and by K. If that's compact, well, the other way that can be compact, K is also compact, remember? So if you just take G mod K, so G mod gamma is just a compact distance from, I mean, yeah, if you mod out a compact group, it can't take something non-compact and turn it compact, that's all. So yeah, that's not too much. Figure that out for yourself. But anyhow, it's clear that if M is compact, then G mod gamma is compact and vice versa. I guess the obvious one is, if G mod gamma is compact, then obviously M is compact, even if K weren't compact. The converse needs the fact that K is compact. So they're compact distance from each other, so if one of them is compact, the other's compact. And then just for terminology, let me just say in this situation, if G mod gamma is compact, well, gamma is a lattice already, definitely, but I'll say that it's co-compact if G mod gamma is compact. That's just terminology that I want to say clear. Okay, so the situation here is that Yeah, okay, yeah. So this is obvious, but now I want to give you something that's not obvious, a way to tell. So this is not very helpful, but except that it means that instead of worrying about K, I'm just going to tell you when G mod gamma is compact, and what that means to geometers, I'm telling you when M is compact. But let me talk about G mod gamma because I'm actually an algebraist. So I'm going to tell you when G mod gamma is compact, or actually it's easier to write down when it's not compact. So I'll tell you a simple way to tell whether or not G mod gamma is compact, and that's the same as telling you how to figure out whether or not M is compact. And the condition, I said it's simple, it's not simple, but it's group theoretic, so it seems simple to me because I've studied groups. But anyhow, G mod gamma is compact if and only if, G mod gamma fails to be compact if and only if you can find an infinite sequence of elements of G and an infinite sequence of elements of gamma, except actually I want all those elements to be non-trivial, not the identity. So let me put it, so these gammas should be non-identity elements of gamma, such that, well, I said it was simple, but maybe it's not so simple. I guess it's not so hard to find infinite elements of G and infinite elements of gamma that have some condition. The condition is, if you conjugate each gamma by the corresponding G, so take G inverse gamma G for each one of these gammas, every gamma has a G that corresponds, so for every gamma I get some other thing. Well, if G mod gamma is not compact, then you can pick your gammas and your G so that these things have a limit, and that limit is the identity. That's exactly what it means for G mod gamma not to be compact. And I probably shouldn't have said this was an easy condition, but anyhow, it's a true condition. This is one way to tell whether or not G mod gamma is compact. And let me prove that. So let me just quickly remind you, this is what I want to prove. G mod gamma is not compact if and only if you can find a sequence of G's and a sequence of gammas, so that when you conjugate each gamma by the corresponding G, the limit is the identity. Right? Or maybe I should, actually, before I do that, I should ask this. I'm about to prove this, so let me ask, is the statement clear? Is there a question about what I'm going to prove? All right, so let's go ahead and prove this, except I'm only going to prove one direction, just at least to give you the idea that this has something to do with G mod gamma not being compact. Okay, I'm just going to give the idea of it. And the proof is by contradiction. So I'm trying to prove that G mod gamma is not compact. Let's suppose it's not true that it's not compact. Well, that means let's suppose it is compact. And I'll get a contradiction. Okay, so let's pretend G mod gamma is compact. What that means is that all of G is within a bounded distance of gamma. Oops, sorry, that's next thing. First I want to introduce some notation. I'm doing these conjugation things. Let me have a notation for that. So I'll just write a to the b to mean the conjugation of a by b. That'll just mean, oh, except I wrote the wrong thing. Shoot. All right. Yeah, so that's completely wrong. Ignore what I wrote there, please. A to the b means b inverse ab. I got the letters mixed up there. I apologize. So, all right. Yeah, so a to the b means b inverse ab, and now I probably have it wrong here. That's the conjugation of a by b. Okay. We're taking a and conjugating it by b. So in this right over here, this whole thing here, I mixed up my a's and my b's. And that was, this wasn't taken. Okay, yeah, so that's just a notation. This is, the point is that that's a lot to write, so let me just write it shorter. This is standard notation in group theory, okay? So now I can say, we're assuming that G mod gamma is compact. That means that every element of G is within a bounded distance of gamma. Well, what that tells us is that you can write everything in G as something in gamma times a bounded thing, something compact. So you can find a compact subset of G, so that gamma times that set gives you all of G. Everything's within a bounded distance of gamma. Okay. Now, here's the thing. So let me just say a couple of obvious things. First of all, the only thing we know about C is that it's compact. But we also know that gamma, I never said it here, but I'm assuming that gamma is a lattice. So that means that gamma is discrete. And if you take away the one point from a discrete set, you don't suddenly get limit points, it'll still be discrete. So gamma cross, the non-identity elements of gamma is discrete. These are two obvious facts, I hope. C is compact, gamma cross is discrete. Well now, if I take all of gamma cross, the elements of gamma cross, and conjugate them by elements of C, okay, so, oh yeah, I should have said that. Actually, I don't even need the fact that it's discrete, just that it's closed is all I need. If you take all the elements of a closed set and conjugate them by some compact set, well, the way to think about this, I've got conjugation, this function here is a continuous map. and I've got a closed set, and then add some compact stuff to it, the image of this set map is going to be closed. That's the crucial thing. The fact that C is, and here's crucial that C is compact, not just closed. But yeah, because it's a compact set, it's only moving things about a distance, you won't suddenly pick up accumulation points. That, all the conjugates, all the conjugates you possibly get by taking all the elements of gamma and all the elements of C, that will give you something closed. It's a closed set. And now I'm going to do a calculation. Okay, therefore, well, I'm supposed to, I've got these conjugates, I want to show that they're, in fact I'm assuming, that's right, I'm assuming that the limit of these things is the identity. That means that the identity is an accumulation point of the set of all conjugates here. If you look at the set of all these things, the identity is the accumulation point. That exactly means that the identity is in the closure of those points, of the set of those points. And now I'm just going to calculate this closure. Well, actually, I'm not going to calculate exactly. It's certainly, what I've done here, I've taken elements of gamma cross and conjugated by my elements of G. So this is a subset of what I've got here. And so if you take the closure, it's a subset of the closure. And then what I do next? So when I know what G is, I've got a formula. G is gamma times C. So I just use that fact that G is gamma times C. And now I have to use the fact that what I've written here, this conjugation action, is actually a group action. If you take A and conjugate by B times C, that's the same as A conjugated by B, and then conjugate that by C. So I'll just write that here. So here, if you conjugate by elements of gamma, and then conjugate by elements of C, well, that's just conjugate by elements of gamma, and then conjugate by elements of C. So this is the fact that we've got a group action here. And now, this is something I haven't said, but it's not hard to see. If you take an element of gamma and conjugate it by an element of gamma, well, if both A and B are elements of gamma, then the result is going to be an element of gamma. And also, if A is not the identity, then the conjugate's not the identity. So, yeah, gamma cross conjugated by elements of gamma just gives you gamma cross. Everything's happening inside of gamma there, so you're not going to get anything outside of gamma. And now what I know, though, so I've got gamma cross conjugated by C. Gamma cross conjugated by C is closed. So the closure of the closure of a closed set is that set. Right, so I hope all these calculations make sense. And then it's just an observation here. I'm taking elements of gamma that are not the identity and conjugating by stuff. Well, if you take a non-identity element, its conjugate will never be the identity. The identity is certainly not in this set right here. On the other hand, I said it was in that set. That's the contradiction. Okay. So I pretended that G mod gamma was compact. I found that the identity is both in and not in some set. I got a contradiction. So in fact, as I hope, G mod gamma is not compact. And so I don't want to give the proof of the converse the other direction because that'd take some time, but I want to at least give the idea of why these conjugates have something to do with being not compact. And the other direction isn't hard, but it would take a little longer than this, and I'd rather do some other things instead. But I hope you have the idea now that certainly these conjugates have something to do with being compact. All right, so what we know is that G mod gamma is not compact if there do exist these things that go to the identity. Right, that's what I'm saying. Yeah. Okay, so let me just remind you. So what we've just proved is that G mod gamma is not compact if there's a bunch of things that tend to the identity. And what I want to say is that that actually is useful. Let's just apply that to learn about something about a space, and it'll be basically the easiest example I can do is let's just take the simple Lie group, SO2, SO2R. Well, I guess maybe to you, SO13 is simpler, but to most people, 2x2 matrices are easier than 4x4 matrices. So let's just take G as SL2R. Gamma will be the integer points of SL2R, so that's SL2Z. This quotient is a finite volume locally symmetric space, and it's easy to see from this condition that it is not compact. That's what I want to explain. I want to explain how to use this condition to actually see that a manifold's not compact. So let's go ahead and just do the calculation. The point is, I need some G's and I need some gammas. So the G's, I'll just choose diagonal matrices. And I need a G sub, so for G sub I, I'll just put an I on the diagonal. Right, so G sub I is an I on the diagonal, but SL2R means I need determinant 1, so that means I have to put a 1 over I down there. So I just put a number there, 1 over to make determinant 1, and then gamma I, maybe this isn't obvious, but instead of being diagonal, I want it to be upper triangular, strictly upper triangular. So I put 1s in the diagonal, and gamma I, actually all the gamma I's are the same. Excuse me. I'm allowed to have gamma I depend on I, but I won't bother. I'll just take the same Gamma 1, gamma 2, gamma 3 are all the same thing. And then we just have to do a calculation. I want to calculate G inverse times gamma, G inverse gamma G. So I'm going to calculate. So let's just write that down. Here's G. The inverse of this matrix will just have a 1 over, it'll just switch the 1 over I with the I. It'll have a 1 over I there and an I there. That's G inverse. Yeah, that's G inverse. If you multiply these two matrices, I think you can, it's exercise to see that multiplying those gives the identity. And then we have gamma I is just given there, and then GI is also given there. So it's gamma I inverse, GI inverse, gamma I G. If you multiply these out, well, just believe me or do it right now. If you don't have anything else to do, just go ahead and multiply these three matrices. I think I got it right. Okay, I'm pretty sure I got that right. These matrices have a limit. As I gets large, well, 1's not changing, 0 is there. This thing here tends to 0. And that is the identity matrix, which in group theoretic terms, that's the identity element of the group. So GI inverse gamma I GI tends to the identity. I found a sequence that does that. By the compactness criterion, I found such elements, that means that G mod gamma is not compact. That's a basic example of using this compactness criterion. The trouble with it is that you have to find these GIs, you have to find infinitely many G's and infinitely many gammas, then you check that they work. So this is absolutely correct. The trouble is it's not very easy to use. So let me give you a simpler condition that's easier to use. But before I do that, let me just rephrase this. Oh, no, I guess, okay, let's keep that thing the way it is. Oh, yeah, I should have said that. So this shows, we know that SL2R mod SL2Z is not compact. Well, same thing. The same proof shows SLNR mod SLNZ is not compact. Except, I guess, you have to assume N is at least 2. SL1R is trivial, I think, right? So then it's obviously compact. Yes?
Is there an easy argument to use that SLNZ is a finite volume?
Oh, is there an easy, the question I think was, is there an easy way to see that SLNZ has finite volume in SLNR? That was your question? No, I don't think it's easy. I think the only way I know is you construct a set C that's not compact. But yeah, so I should have said that. To show that this has finite volume, what reduction theory does is construct a set C that has, it's a set C in G. It's in G, it's not compact, but it does have finite volume as a subset of G, and you prove that gamma times that set is all of G. But to construct that set, you do what's called Siegel sets. I don't know anything easier than using Siegel sets. Maybe, I guess, well, there is an alternate approach using Ratner's theorem, but I certainly wouldn't say it's easy. Yeah, no. Unfortunately, this is a very important fact that the quotient has finite volume, but it's not something I'm going to prove. If I wanted, I guess if I took a full hour-and-a-half lecture, I could probably do it. But I didn't want to do just one thing in an hour and a half. I want to do lots of things instead. Yeah, it's unfortunate we just have. So in my book on arithmetic groups, I just take it as an axiom that G mod gamma has finite volume because it's an important fact, but it takes too long to prove. Okay? Yeah. I'm sorry that I can't tell you that, but at least I can tell you it's certainly not compact, even if it was finite volume. It's definitely not compact. All right. Yeah. And so let's. So that's the condition we've got. Yeah, we've got a condition for telling when M is not compact. The trouble, though, is that it's, I guess there's two things. First of all, it's not easy to use, but even worse, probably, is that it's purely group theory. You have to find these G's and conjugate them and take lists and stuff. Here's a simpler way. I can rephrase this in terms that's easier to check in many cases. All right, so I'm going to rephrase this condition. We know how to tell that something's compact, but let me rephrase it. Well, I'll give a condition for saying that G mod gamma is compact. If you want to check whether G mod gamma is compact, well, this condition says, check to make sure that there's no G's and no gammas that have this property. Well, here's an easier thing to know. G mod gamma is compact if and only if gamma has no unipotent elements. And let me tell you what unipotent means. Okay, so all it means is that an element, a matrix, is unipotent just means that if you take U minus the identity, well, saying that U is unipotent means that U minus the identity is nilpotent. Some power of U minus the identity is 0. That's what a unipotent matrix is. When you subtract the identity matrix, it becomes nilpotent. The power of it will be 0. But that's maybe not the best way to say it. Another way of saying the same thing is that, U minus the identity equals 0. Well, if you think about it, this tells us that the only eigenvalue of the matrix U, when you subtract off U, it becomes 0, so the characteristic polynomial of U minus the identity is just all zeros. So the characteristic polynomial of U, well, I don't know how to say this, but I'm botching it up there. The only eigenvalue is 1. That's exactly what it means. If you've got a matrix, and the only eigenvalue it has is the number 1, then it's unipotent. And another way of saying it is, well, as I said yesterday, every matrix can be put in upper triangular form, and when you do that, you get the eigenvalues on the diagonal. So if the only eigenvalue is 1, then after you do a change of basis, the matrix will just have 1s on the diagonal and be upper triangular. So this maybe is the easiest way to think about it. A unipotent matrix is a matrix that's 1s on the diagonal and 0 below. You can have whatever you want up there, but that's after you do a correct basis. In some basis, you can make this purely upper triangular with 1s on the diagonal. That's what a unipotent matrix is. Okay, and so the condition, I claim, that you can check whether G mod gamma is compact just by checking whether or not gamma has any matrices like this. And so let's prove this. Whoops, I should have said here, so yeah, I have to say this right. Okay, let's make sure we're clear on this. G mod gamma is compact if gamma does not have unipotent matrices, but for the proof it's easier to do it the other way. So G mod gamma is not compact if gamma does have unipotent matrices. Okay, so let me say it that way. I'm going to say it here. So G mod gamma is not compact means that gamma does have unipotent matrices. And I guess I didn't say it quite right. Every group has a unipotent matrix, the identity matrix. What I meant was non-identity unipotent matrices. Okay, I'm not interested in the identity elements of the group. But that's the condition. So this is just saying the same thing, but I guess I said the contrapositive. So this is what I'm going to prove. In fact, this one will prove both directions, but let's start by, if G mod gamma is not compact, let's show that there's unipotent matrices in gamma. There's a matrix that has no eigenvalues other than 1. And the key is that we already know what it means to say G mod gamma is not compact. If G mod gamma is not compact, then there are these G's and there are these gammas, so that when you take the limit, you get the identity. That's the condition we already have for compactness. And now I need to look at these gammas a little bit more carefully. Well, even before I look at the gammas, let me just look at the identity. Okay, so I'm just going to say some basic, obvious facts, I think. The characteristic polynomial of an identity matrix, well, the characteristic polynomial of any matrix is the determinant of lambda times the matrix minus the identity. So the characteristic polynomial of the identity matrix is just the determinant of lambda minus the identity. Okay? And that determinant is just lambda minus 1 to the nth power. That's the characteristic polynomial of the identity matrix. And now the next thing to notice is that these gammas are all integer matrices. And if you take the characteristic polynomial of a matrix that's only got integer entries, well, you're calculating some determinant, and the only things in the matrix that you take the determinant of are the variable is there, lambdas are in there, and some integers. The determinant to that will just have lambdas and integers in it. All the coefficients of every lambda will just be an integer. So the characteristic polynomial of this matrix only has integer coefficients. Everything involved is an integer. And then the next thing we need to notice is that it's a basic fact that similar matrices always have the same characteristic polynomial. And here, gamma I, well, gamma I is certainly a similar matrix to this nest there, so let's look at that. This GI inverse gamma I is conjugate or similar to gamma I, so that's the same characteristic polynomial as gamma I does. But the characteristic polynomial of gamma I is integer coefficients, so the characteristic polynomial of this thing here has integer coefficients. And then the last basic thing I have to notice here is that this characteristic polynomial, right, so of this element here, well, this sequence of matrices converges to the identity. So the characteristic polynomial, I guess what I'm saying is the characteristic polynomial is a continuous function of the matrix. So if the conjugates converge the identity, then the characteristic polynomial has to converge the characteristic polynomial of the identity, which we know. Where's here? Yeah, the characteristic polynomial is just lambda minus 1 to the n. Okay, whoops, oh sorry, I'm going to get back in a minute. Yeah, okay, so the characteristic polynomials converge, but there's one more thing that we already said here. This characteristic polynomial has integer coefficients. That characteristic polynomial, it's right here, it also has integer coefficients. So I've got a converging sequence of integers that convert, I've got a bunch of integers that converge to an integers. The only way that can happen is that they actually get there. It's not, you've got a bunch of integers that are close within epsilon of a bunch of other integers. In fact, they have to be exactly equal. They have integer coefficients. So the characteristic polynomials, they can't just be close. If they're close, they're actually exactly the same. So the characteristic polynomial of this matrix is exactly the same as the characteristic polynomial of the identity matrix if I is large. And what that means is, well, we know the characteristic polynomial of the identity matrix. The characteristic polynomial of this thing is the same as the characteristic polynomial of that, but that's got the same characteristic polynomial. Where did I say here? Somewhere I said, we have the same characteristic polynomial. The characteristic polynomial of gamma is just the characteristic polynomial of the identity. So I said this badly, but the point is, this matrix, we know the characteristic polynomial of, it's that, but these are similar matrices, so they have the same characteristic polynomial. So that's it. The characteristic polynomial of gamma is this matrix here, but the eigenvalues are the roots of the characteristic polynomial. And so what are the roots of this polynomial? It's obvious. The only root is 1. Okay? So the only eigenvalue, the only root of that polynomial is 1, and that's exactly what it means to say that that gamma I is a unipotent matrix. So if G mod gamma is not compact, then by this limiting argument we see that there's a matrix in gamma that has only 1 as its eigenvalues. And that's because there's a matrix, the way to think about it, there's a matrix not in gamma but conjugate to an element gamma that's close to the identity. That's all this. So the characteristic polynomial has to be the same as the characteristic polynomial of the identity matrix. Right, so that's a crucial fact. But let me prove the converse. Okay, so we got here, so this statement, it said when G mod gamma was not compact. Yeah, and let's just add. So the point is we now know that if G mod, we've done 1/2, we proved that G mod gamma is not compact, then there's unipotent elements. I want to prove the converse. So I want to prove that if there are unipotent elements, then G mod gamma is not compact. And the proof is actually quite easy, but it's easy if you know a fact from Lie theory. Okay, so I just have to state a fact about Lie groups, and once we have this, it'll be easy to prove the converse direction. And the fact I need is called the Jacobson-Morozov lemma. It says that if you have a unipotent element of any group G, well, G I'm assuming is a semi-simple Lie group connected, and so it's a group of matrices, okay? But technically I need it to be semi-simple, but remember, in the situation we're in, all G's are semi-simple, because we're talking about no compactors, no flat factors, right? So if you have any unipotent element of G, then there's a homomorphism, and all homomorphisms are assumed to be continuous. It's a homomorphism from SL2R into G. Well, it's easy to find a homomorphism that maps SL2R into G. But the key thing is that this SL2R has unipotent matrices. In fact, I gave you the one. It's just a 1 on the upper. There's an obvious unipotent matrix in this map. You can map that obvious unipotent matrix onto that arbitrary unipotent element of G. Every element of G, every unipotent element of G just looks like this one given unipotent element of SL2R. So inside of G, you can find an SL2R that contains U, and in fact, U is just that matrix. And then once you've got that, it's easy to complete the proof. The proof of the converse statement there is just, well, okay, I'm assuming gamma has a unipotent element, so just let U be some unipotent element of gamma. Okay, I'm sorry. Let U be a unipotent element of gamma, and let's just let all of our gammas be that element U. So just you let all your gammas be some unipotent element of the group gamma, which we're assuming exists, and then I need to give you some GIs. Well, once you have this U, we can apply the Morozov lemma to get a homomorphism from SL2R into G, and apply rho to the element of G that the G we used before, to the diagonal matrix. And before, when I showed that SL2R mod SL2Z was not compact, I took this G and that, this G and that U, and showed that the limit was the identity. Well, if you apply a continuous homomorphism to a sequence that converges the identity, it'll still converge the identity. So the fact that these two elements work in SL2R means that rho of them will work in will work in G to show that G mod gamma is not compact. And that's, I think, a good place to stop here. We now know how to tell whether or not a group is a manifold is compact. I'll do some examples of that as soon as we finish our break. So let's just take 5 minutes and then continue. Okay?